Well, good good morning, Thermo students. Nobody's here yet. Well, maybe you'll show up. It's only 8:23. Let's give you a little bit of time to show up here. Unless they've had a time change that I didn't know about. Okay, July 1st. Topics for today. Oh, hey, we've got a customer. Stuart, welcome to Wednesday morning Thermo. We have Stuart. Wonder if we got anybody else. Yes, we have Spencer. Welcome, Spencer. Why don't you guys say hi?
Hello. I have a question real quick.
Sure.
When do you think you're going to have the video for Monday's lecture posted? I wasn't able to make it Monday, and I'd like to have that before I get started on the homework that's due tonight.
Yeah. Let me go check with my IT person. One tiny second. Okay, now let's see. Was I talking to Spencer? Is that who I was talking to?
Yes, sir.
Spencer, I just talked with my IT person, which is my daughter. See, what I need to do is just go to a younger person whenever I need help on this computer stuff. She says that she will put it on there today. They haven't done it yet,
All
but
right.
it'll be on there today. Now I don't know what today means exactly, but it'll be on there today.
All right.
Thank you for asking, and we'll make sure that's on there. Is there? Hey, we have another customer, Cameron. Welcome.
Hello.
Cameron, I got your exam. Can you make them right side up instead of sideways for me?
Yeah, I noticed that. I can try. I'll try to fix that next time.
It's okay. I figured it out, but I have to turn my head horizontal to read your stuff.
Put a crook in your neck.
Yeah. I'm sure there's a button to push to make it turn it upside
Yeah, I
right.
didn't realize it was going to do that when I sent it.
It's not the end of the world. Okay. Was there any other? Oh my, we only have a couple of minutes and we're going to get started on our exciting material today. But was there any? Oh, look, to Parker, welcome. Was there anybody else that wanted to say anything before we launch into the exciting world of? We have two big topics today. There's isentropic processes, and then there's the second law for control volumes. That ought to keep us busy for a while. But was there any other comment before we get started? Well, okay, well, if you don't have any comments, and that that video from Monday and for today, I'm sure both will be posted on YouTube when my IT person gets home from work. She can do that. Today's her birthday. She's 30 today. She's my youngest. My oldest is well, she's 51, I guess. Yeah. I think that's right. Either that or 52. Yeah, I think she was born in 69, so that means she's 51. But my youngest is more your age. She's 30 today. Okay, well, it's time, and we're going to get started now. The first big the first big topic is isentropic processes. Now, what does that mean? We'll get to the second law here in a little while, but what does that mean to have an isentrope? Well, it might have something to do with entropy, don't you think? Yeah. Can you kind of see that word entropy kind of hidden in there? And you all know what this iso this and iso that means. This means constant entropy. What it means is the change in entropy would be zero. That's what an isentropic process is. And the second law, now this I believe was on Mondays. That's why I think it was Spencer maybe that wanted to see the video. It's explained beautifully on that Monday video, which we will post sometime this afternoon. The second law goes like this. Now, if the change in entropy is zero, that must mean that this term will be zero And this term, well, let's put it this way. If this term is 0 and that term is 0, then you got 0 plus 0. Hey, that gives you 0. And so you have an isentropic process. Now, for this term to be 0, what it would be required here, let me, I'm always picking on Stuart, but I don't know if he's with us. Yeah, Stuart. Yeah, Stuart's with us. Stuart, I want you to answer this question. If this term here is 0, how could that be, Stuart? How could you get this term to be 0? What do you think? He's thinking. We're going to make that term 0. How do you make that term 0, Stuart? Debunk? No, that's not the word. Demute. Unmute. Stuart, unmute and tell me how you get this term here to be 0. Uh-oh, he's still fixing his coffee. Never mind. He's busy. One way is if the heat transfer is 0, then this is going to be 0. Now they have a fancy name for that. If the heat transfer is 0, they call it Stuart wasn't going to help me. Let's go to my friend Spencer. Unmute and tell me, what do they call it when there's no heat transfer, Spencer?
Would it be isothermic?
No, let me talk about that. That's confusing to students. See, it's what I was after, Stuart, was adiabatic. And I told you guys about this, but do not get adiabatic and what you said made sense. Do not get confused between adiabatic and isothermal. Because, see, adiabatic is when Q is 0. Isothermal, you don't have to have Q be 0. In fact, think about boiling some water. And now who am I talking to? I'm talking to, who am I talking to now?
Spencer.
Yeah, Spencer, thank you. Spencer, go to your kitchen, put some water on, and boil some water. Now that's isothermal. You know water boils at what, 212 Fahrenheit?
Yes.
And you just boil it there for 30 minutes. And guess what? The whole time that you're got the fire on the stove and or maybe it's electric, whatever, you're transferring heat into that water and boiling it. So the Q is not 0, but the temperature stays the same. Adiabatic is different. Adiabatic is the Q is 0. Now, an example of that would be if you had a bicycle pump and you push down on the handle there on your bicycle pump. See, what you're doing is you're compressing the air, and it gets hotter. If you tell you what you do, get a bicycle pump and pump up your tire. Push on that bicycle pump for about 100 times, and it doesn't do a heck of a lot to a car tire. You'll go from about 30 to 35 psi. I've done it before, but it'll take you about 100 pushes. You'll be wore out by the time you get 5 psi more in your tire. But see, it's adiabatic. The temperature is changing. You can have a change in temperature, but the heat transfer is 0. What's making it hot is all that work. See, there's work transfer, there's heat transfer. They're different. And pushing on that bicycle pump, you're doing work and you're compressing the air and the air gets hotter. I hope you guys aren't confused. If you are, ask me something. But there's a big difference between adiabatic and isothermal. Now, if this Q here is 0, well, then this term is 0 because you're just dividing by what, Kelvin or Rankine temperature, and it's never 0 unless you're awfully cold in outer space. So here's how you can get an isentrope. You can have an adiabat. That makes this term 0 if you have an adiabat. Now, how do you make this term 0? Let's go to one of my excellent students here. We're going to go to Parker. I think I was trying to pick on Parker earlier. Parker, this here is called generated entropy. How do you make generated entropy 0? Unmute.
If it's a reversible process.
It's a what?
It's a reversible process.
Yeah, that's it. Exactly. Yeah, you can make that 0 if you have a reversible. You know, you guys could read all this stuff in the book. This is all in the book. But I don't know if I explained that good, but there's a whole several pages about that stuff in the book. I wonder if I could tell you where that is, about reversibility and irreversibility. I've told you a lot of stuff already. You know, if you have friction, then it's irreversible. Yeah. Here they are. There's on page 153. It says factors that render processes irreversible. Friction is the first one mentioned. Then they have unrestrained expansion, heat transfer through a finite temperature difference, mixing, and other factors. So there's a whole bunch of things that can cause irreversibilities. But if you have a reversible adiabat, then you've got an isentrope. Let me write that down for you. See, if you have delta S equals 0, that's what an isentrope is. And another name for an isentrope is a reversible adiabat. Now, I will tell you one little tiny wrinkle. It's possible to have an isentrope and these aren't 0. Now, I'll tell you how that'll happen. If this is negative, let's say this comes out to be -5, and this comes out to be +5. This is just an example. Well, you know what? -5 and +5, that could give you 0, couldn't it? So it's possible to have an isentrope that is not reversible, because if this is +5, that's not reversible. And if this is -5, that's not an adiabat. Remember the rules about generated, let's go over those rules. Generated entropy. If it's 0, then you have a reversible process. If it's bigger than 0, you have an irreversible process. If it's less than 0, it is impossible. You have just violated the second law of thermodynamics. So it's possible to have an isentrope that's not an adiabat, but you're going to have a heat transfer out in order for that to happen. Well, now we're going to examine this a little further. Unless you have a comment or question, we're going to see what happens if you have an isentrope with an ideal gas. Did you have any comment before we tackle that? Did that make sense to everybody? Well, I'm hoping it did. Okay. Now what we're going to do now is we're going to talk about an isentropic process with an ideal gas. Now you can have an isentropic process with steam or refrigerant or ammonia or pretty much anything. But right now, we're going to be talking about what happens if you have an ideal gas, isentropic process. Okay, do you remember we derived this equation? I showed you this equation. I don't know whether this was Monday or not. Hey, I'm going to go with little letters. You can write this with big letters, or you can write it with little letters. The little letters are really better. We derived that equation from those Gibbs equations, those TDS equations. We derived the TDS equations, and then we derived this equation here for the change in specific entropy from those TDS equations, or some people call them the Gibbs equations. I wonder if anybody remembers that. Let me ask one of my wonderful students here. Cameron, do you remember us deriving this equation, talking about this equation, Cameron?
Yes, I do.
Yay! Good deal. We talked about that. Now, if you had an isentropic process, this would be 0. And so we could write it like this. Now we're going to do some algebra here. You guys love algebra. I know you do. So see if you can get to here with me. Can you get from here to here? Can you make it? Well, I'm hoping you can. Now see if you can get to here. Can you get from here to here? I bet you can. Now keep in mind, this is if you have an isentropic process with an ideal gas. Remember, I told you guys, if you ever see an equation with R in it, that's the ideal gas constant, isn't it? If you ever see an equation with an R in it, you better be working with an ideal gas. Or if you see an equation with a C sub P there, well, that's only good for the ideal gases. Now they do have specific heats for liquids and solids. They do. I don't know if I ever told you this, but liquids and solids only have one specific heat, not two. See, with ideal gases, they have a CP and a CV. Ideal gases have two of those specific heats, but liquids and solids only have one. Did you know that? Well, now you do, because I told you. Okay, now We're doing another algebra step. See if you can get to here now. Now this one is a little tricky, but you guys all took algebra. I bet you can get to there. Can you get from here to here? I hope so. Hope you can see that good. Okay, well, we're almost done and we're going to have a wonderful equation for an isentropic process with an ideal gas. But I need the room. So I think what I'm going to do is I'm going to write this up here where I have some room. And then we'll do an example. Wouldn't that be fun? Now let me write this one up here now. All I did was just scoot it up there where now we got room, and I'm going to just erase all this stuff here for a minute. All you need to know is all that stuff comes from an isentropic process with an ideal gas. Now, I showed you guys this. I don't know if you remember, but see, R is equal to C sub P minus C sub V. I showed you that from scratch one day. We can go back over it if anybody wants me to. We don't have time to go back over and over everything. And so if you had R over C sub P, yeah, then this is equal to, I think I did that right. This is equal to this. See if you can get to there with me. Can you get to here with me? All right, great. I know we talked about this, like for instance, for air. You've all memorized for air, this is 0.287 in the metric. And this is 1004. And this is 0.717. Subtract those and see if I'm lying to you. Here, I'm going to try it. Boy, Juve, it worked pretty good. Now in English, senor, this here is, oh gee. The units are so confusing. I think it's 5334 foot-pounds force per pound mass Rankine, but you'd have to convert it to BTUs. So you'd have to go BTUs 778.17 foot-pounds force. And from memory, I think that's 0.240 BTUs per pound mass. And I think this is 0.171 BTUs per pound mass Rankine. Now let's see if this is correct, okay? See, this is in English. All right, I'm going to try that. I'm going to see if it works. Uh-oh, I don't think it's going to work. Something bad happened here. 53, 34 divided by 778. Well, I'm getting an answer, 0.0685 on the left. I wonder if that's what this is. I don't know. Now, maybe I did something wrong. No, it's fine. Everything's okie dokie. Oh, the only thing is this this rounds off. Somebody rounded something off someplace. I don't know whether it was me or the book or what, but it's okay. In other words, this equation is fine. And we're almost ready to finish our lovely formula that we're talking about this morning. What we're talking about is a formula for an isentropic process with an ideal gas, and we're almost done, almost done. So I'm going to erase this, but that was kind of fun to do. Hey, I didn't put the units on this this deal here. What's going to happen to you if you don't put units on your stuff? See, that's the units. It's kilojoules per kilogram Kelvin. If you don't put units, you're going to lose a point. We don't want that to happen. Supposed to put units on there. Okay. Now, see if you can get to here with me. We're almost done. I keep saying that, and then I can just keep on going, don't I? Can you write it like this? Can you get to here? I bet you can. Okay, 2 more steps. What's this now? See if you can get to here. Now, I'm going to define something called the specific heat ratio. What it is C sub P over C sub V. It's always bigger than 1. It has a fancy name. It's called the specific heat ratio. They've got them in the book back there. If you go back here in the book and look in the tables, I'm looking in the tables. Yeah, I see some K's back there. So I see some K's for a whole bunch of things, for steam, air, ethane, helium, etc. They have these in the tables in the back. They're called specific heat ratios. But see, this is C sub V over C sub P. This is C sub P over C sub V. So what we have here is 1 minus 1 over K. That's what we have. Or you could write it like this. Ta-da! And it took all that work and 2 boards of algebra there. And if you followed through with me, we came up with that equation. And that equation is only to be used for an ideal gas isentrope. But if you have an ideal gas isentrope, it's a nice little equation. And these K's you can look up. See, see for air, for instance, here we'll figure it for air. For air, it would be 1004 divided by 0.717. Well, let's see what that is for air. Boy, Jove, it's 1.4. How about that? For air, it's 1.4. And you could look that up. It's in the back here. Let me tell you what table it is. Let me see if I can find that again. For air. This is table A.5. Table A.5. Look it up when you get time, and you'll see K is 1.4. And they have Ks for everything in there. For helium, if you wanted to find the specific heat ratio for helium, it's what they said, it's 1.667. That's what they have in table A.5. You know what it really is 1.666 to all forever. They rounded it off, is what they did. Okay, we got us a great equation there. And that's a keeper, and we'll be using that on our example we're going to do here in a minute. Does anybody have any comment or question before I continue on with this fascinating topic of isentropic processes? Well, nobody said anything. Okay. Now, there's another equation that that would have been fun for me to derive. See, this equation here, that was derived from this equation here. We took that equation there. I know each of you are taking notes. Anything I write down, you got down in your notes. We took that equation and we did some algebra, is what we did. Algebra. We did some algebra. Oops. There we go. And bingo, we came up with a wonderful equation. Well, there's another equation that this one came from those Gibbs equations, but it's a little different. It goes like this. Now this here, you'd have to watch my video over. I think it was Monday that my daughter's going to put on YouTube this afternoon. We did not do that. I did not derive that one, but I showed you where it came from. It came from the other Gibbs equation, which I showed you where they came from. But see, if you take this Gibbs equation and you do some algebra on it, I'm not going to do that right now because I got too many other fun things for us to do. But it follows the same stuff we just did, and what you'll wind up with is this here. And you got to be careful because you got a 2/1 here, but you got a 1/2 here. And it would be fun for you guys to take that and sort of follow the method that I did a little while ago and see if you could come up with this equation. So let's put those together. I like this. Ta-da, and now we have a really nice equation we can use for an ideal gas isentrope. Ideal gas isentrope. And you know what an isentrope is. An isentrope is when delta S is 0. Okay, well, great. Anybody comment, question on that before we do an example? Well, okay. I thought maybe we could do 651. We're going to do 651. We're going to do problem 651 here in just a minute, if nobody has anything to say. All right. And you know the method for doing problems in here. We do the same thing over and over and over again. We do a device sketch. We do a PV diagram. You're not going to forget a PV diagram, are you? You would not forget that important thing, would you? Did you notice on that exam, I think there was 2 questions that required a PV diagram. And now we're learning to do TS diagrams. So from now on, for a while at least, do both. Do both. Okay, well, let's do that. And then what? After you do the device sketch and the PV and the TS diagrams, then what? Well, you use the first and second laws. That's what you do. You use the first and second laws. And you got to decide now, is it a control mass or is it a control volume? And you know the difference. You know what a control mass is and what a control volume is. All right, well, let me find this 651 and we'll do that. That sounds like fun. Here we go, 651. I just wonder if you really do know the difference. I'll pick on somebody here. Let's see. Roxana, you're a good sport. Tell the others the difference between a control mass and a control volume. Go, Roxana. Control mass, control volume. Roxana is going to tell us the difference. Go for it, Roxana. Unmute. Earth calling Roxana. Earth calling Roxana. Come in, Roxana.
I think one of them was no mass transfer, but it has
Yes.
a change in volume.
That's right.
And then the other has mass transfer, but the volume is fixed.
You are perfect except for the volume is fixed. The volume strangely enough, on a control volume, the volume can change. It does not have to be fixed. I wish they didn't call that. Other books call this closed system, open system. I think I like that better. But you got the important thing right, Roxana. The control mass, there's no mass going in and no mass going out. But with the control volume, you have mass coming in and usually mass going out. But you have one or the other. You have mass coming in or out. You might just have mass going out. Well, let's see what kind of problem this is. This is 651. Okay, a piston cylinder. All right. Let me draw the device sketch. Okay, here we go. Device sketch. Piston cylinder. Here's state 1. Here's state 2. Air at 1,000 kilopascals. Okay. 1,000 kilopascals. Piston cylinder. Got a heavy weight on there. Got air in here. 1,000 kilopascal. State 1. Now state 2 is 100 kilopascals. I think my guess is they took that weight off. When you take that weight off, you got 100 kilopascals. The pressure goes down, and I think the volume would probably go up. Let's read this here. Now this starts off at 800 K. Now we don't know what T2 is, but my guess is it's going to be colder. It's just the opposite of compression. See, when you compress things, they get hotter, but this is not being compressed. This is going from 1 to 2. Now let me keep reading. Final print. Consider 2 different processes. Reversible adiabatic. They want us to do a reversible adiabatic. They want us to go from state 1 to state 2. This is part A, I guess. Part A, they want us to do a reversible adiabatic. Now we've learned this morning there's a fancy name for a reversible adiabatic. We've learned that. And I'm going to pick on Parker, I think. Let me see if I want to pick on Parker or not. Yeah, I'm going to pick on Parker's a good sport. Parker, we learned a fancy name for a reversible adiabatic. What is that fancy name, Parker? Unmute.
I'm not sure.
That's okay. That's why I bug you guys. Because if I bug you, you'll get it. Parker knows this. It just hasn't penetrated. That's all. Parker, this is called an isentrope. Have you heard that word before, Parker? Isentrope. Parker, say yes. He had to go answer his front door, I think. But if you have a reversible adiabatic, you have an isentrope. Now, What's an isentrope? Now here, let me pick on my next wonderful student. Cameron. Cameron, what is an isentrope? You tell me, Cameron. Unmute. What is it?
I'm not too. I don't think I'm too for sure, honestly.
That's okay. It's early in the morning and it's sometimes you have to wake up. We're gonna go. I know somebody must have listened to me. How about my friend Aubrey? Aubrey, what is an isentrope? Unmute. Tell everybody what an isentrope is. See, that's what
Is
we've
it where
been.
where the delta S is equal to 0?
Yay! Good for you. Good for you, Aubrey. It's when delta S is 0. That's what an isentrope is. And if you if you have an isentrope and it's reversible and it's an adiabat, then you can do this. Now we know what T1 is. T1 is 800K. And we know what P2 is. And we know what P1 is. And if it's air, we know what K is. So we can get T2 from this equation. Now I'm going to shut up for a minute and a half. And I want you to do that. This class here is a participation class. You don't need to just sit and watch me do stuff and have all the fun. I'm going to shut up. I want you to find T2. Go for it. Get your calculators out. Okay, I got an answer. Let me go and go fishing here for a wonderful student. How about my friend Cameron? Cameron, did you get that T2 yet?
If I typed everything in right, I got 414.357.
That's what I got. I got 414. I got 0.4 if you rounded it off. Is that close enough to yours, Cameron?
Yes.
Great. Hey, we just got T2. It's 414. Let's do our PV and TS diagrams now, shall we? Doesn't that sound like fun? If you're all okay, I'm going to erase it because I need the room to do the PV and TS diagrams. Hey, it got colder, like I said. You see, it's just the opposite of compression. When you compress, it gets hotter. When you expand, it gets colder. Now, let me ask you this, though. I usually do heat transfers in red. Let's put a red heat transfer. There you go. And let's go to one of my excellent students here. Aubrey, what's the heat transfer on this reversible adiabatic process, Aubrey? What do you think? Heat transfer, what do you think? Unmute. Tell us what you think the heat transfer is on this reversible adiabatic process. Going in or out?
Sure. Oh, it's going out.
She says, Aubrey says it's going out. Nope, it's not going out. Guess again, Aubrey. What's the heat transfer on this reversible adiabatic process, Aubrey?
Then it must be going in.
Nope, it's not going
What?
in either.
Oh no.
I want you to think what the word adiabat means.
Oh, adiabatic. Q equals 0.
Yeah, that was not very nice of me, was it? That was a mean trick. There is no heat transfer. It's an adiabat. There is no heat transfer. Now let's, but see, maybe Aubrey will remember that now. I bet she will. Now let's draw the PV and TS diagrams. Here we go. Okay, now you're more familiar with the PV diagram. Now this is air, so you don't want a vapor dome. Don't put a vapor dome. It's air. I tell you what you could do though. You could go 800 Kelvin. You could have an 800 Kelvin, and you could have a 414.4 Kelvin. You could have those. That'd be okay. And the pressure at 1 is 1,000. So here's state 1, 1,000 kilopascals, and here's state 2, 100 kilopascals, and here's your process. Yeah, there you go. There's your process. See, they call that a process. We are going from state 1. And here's some of the properties of state 1. There's the pressure, there's the temperature. And we're going to state 2. And here's some of the properties at state 2. You have the pressure and the temperature. And you draw, it's not a straight line. It usually isn't. Sometimes it is. But in this case, it's not a straight line. That's the process on a PV diagram. Now let's do a TS diagram. We've got to learn how to do TS diagrams. You don't put a vapor dome in there because it doesn't liquefy, it's air. At the temperatures and pressures like that, it doesn't liquefy. And now let's put in our isotherms. They're flat. See, the 800 goes like this. There's your 800. And then the 414 goes like this. There's the 414. And now for the pressures. Well, pressures on a TS diagram, they're like this. They go like that. This is the high pressure. This would be the 1,000 kilopascals. This is the low pressure. This is 100 kilopascals. I need let me doctor this up just a little bit here. There. Yeah, there we go. And now here's our process. Here's state 1. Here's state 2. And it goes straight down. There's our process. And you notice it goes straight down because the entropy doesn't change. Remember? Delta S equals 0. It's an isentrope. This process is an isentrope. So it has to go straight down. See, if it curved off to the right, that means the delta S would be positive. If it curved off to the left, the delta S would be negative. So what? Well, let's finish the problem. They wanted something else, I think. If you just woke up from a daydream, we were doing 651. Let me read it here. Piston expanded. What are we supposed to do? PV2. Find the final temperature. Well, we did that. And the specific. Okay, now they want the specific work. Here's what they want us to do. They want us to find that little w there. Okay. Well, we have an equation for that. Now, we have an equation for little w that goes like this for polytropic processes. This is an isentropic process, but let me show you the equation for the polytropic process. It goes P2V2 minus P1V1. Now, I showed you this. In fact, I derived that equation for you guys. And what we have here is it's a polytropic process where n is equal to k. N is equal to the, what do they call that? The specific heat ratio. Now, how do I know that? How do I know that? Let me come back to that. Let's go ahead and solve this, and then I'll try to explain how come we know that. Now, I'm too lazy to actually put those numbers in. It's a lot easier for me just to go R T2 minus R T1. And in this case, you go 1 minus K. See, P2V2 is equal to RT2. And P1V1 is equal to RT1. So basically, we're just going R delta T all over 1 minus K. Okay, well, let's do that. Now, R for air is 0.287. Probably should put our units in there. And the change in temperature, I can't do that in my head. But I can subtract. Did I do that right? When you subtract that from 800, is that what you get? I think so. So what you get here is 385.6 divided by 1 minus 1.4. Okay, we're going to get the work done. Here we
Wouldn't
go.
the 385.6 be negative?
We
We're going from a
have
higher temperature to a lower.
we have our first honkin' thank you point. And who was that, my friend?
That was Spencer.
Spencer gets a honkin' thank you point, right? You guys see that big, thick thank you point for Spencer? He's absolutely right. It's negative, and now we're going to solve this. Here we go. Thank you so much. It's kind of weird, but I get a positive answer. How about you guys? Because the numerator and the denominator are both negative. But we can tell that the work is going to be positive because we know that the area under that graph is the work done. And we are expanding. And so we think that that's the work done. I wonder if that's what I got when I did this. Yeah, we did that right. 276. Good going. It turns out this W here came out to be 276 kilojoules per kilogram. Yay! And we did a PV and a TS diagram. And now let's keep going and finish this problem now. We're not done yet. It said here something about consider two different processes, a reversible isothermal process. Okay, well, let's do that. Well, if you had an isothermal process, I'm going to have to fudge this just a tiny bit to show you this. If you're going to go from 1,000 to 100, you're going to have to go to here. I don't want to call it state 2. Let's call it state 3, okay? And here's our process from 1 to 3. But see, that's an isothermal process. See it? That's an isothermal process. Now it goes from 1,000 kilopascals to 100 kilopascals, but it doesn't go the adiabat. This here that's the adiabat. You see that one there? That's the adiabat. Now I think I told you guys that adiabats are steeper than isotherms. See, here's your isotherm. Here's your adiabat. Can you tell that that adiabat is steeper? It's steeper. Adiabats are steeper than isotherm. Okay, now they wanted us to find the work. Well, now the work there, it's going to be bigger. Can you tell it's going to be this area here? Here, I'll color it in. See, it's a huge area. It's bigger, isn't it? Now, how do you do that? Well, we need some room here. Now, let me make some room and we'll do that. It's a different formula. What we're talking about now is a polytropic n equals 1. What we just did was a polytropic n equals k, but this is a polytropic n equals 1, and the equation goes like this. We derived this from scratch too, if I remember right. That's the equation there. Now we don't have the V2 and the V1, but I'm too lazy to figure them out. We could get them. We got enough info to get them, but I think I'm going to be lazy and do this. We know from the ideal gas law that P2V2 is equal to RT2. And P1V1 is equal to RT1. Now, if you divide it equals by equals, you could get V2 over V1. Maybe I should have gotten those. I don't know if this is that much easier. But V2 over V1 is going to equal, well, the R's cancel, and you'll have T2, which is 414, T1 is 800. But then don't you have to go P1 is, don't you have to have 1,000 in the numerator and 100 in the denominator? I don't know if that made sense. It's just algebra. But we can get it. And see, if you're lazy, you could call this RT1. Natural log. And I can get this. Let me do that real quick. Let's see what that is. 14.4 times 10, right? Yeah. And you take, when I did all that, I got 5.18. This stuff here turns out to be 5.18. And now we're going to solve it and get the work per mass on that isotherm. Here we go. All right, natural log of that times, and what's T1 again? Well, T1 and T2, well, now wait a minute. They're both the same. No, this is wrong. No, this is wrong. T1 and T2 are the same. I made a mistake there. It's true that P2V2 is equal to RT2 and P1V1 is equal to RT1. But if you're going down an isotherm, the T2 and the T1 are the same. And so P2V2 is equal to P1V1. See, there's that 1 there on your polytropic thing. So V2 over V1, I made a mistake, but I found it, is equal to P1 over P2, which is equal to 10, I think, isn't it? P1 over P2. Yeah. It's equal to 10. So here we go. The work per mass going down your isotherm now is equal to 0.287. No. Yeah. P1, V1, RT1 is equal to 0.287 times 800 natural log of 10. Right? I think so. Okay, let's do that. Let's see. 0.287 times 800 times the natural log of 10 is equal to, I'm getting 528.7 kilojoules per kilogram. Now, is that what I got when I did this before? Let's see. 520. Yeah, that's what I got before. Do you see this big area here? This big area is 528. 528 kilojoules per kilogram. Whereas this little area here, see this little area here going down the isentrope? It's 276. Hey, you know what? 528 is bigger than 276, isn't it? Now, we haven't drawn it over here yet. See, this from 1 to 2 is your isentrope, and from 1 to 3 is your isobar. Now, this from 1 to 2 is your isentrope. Now, where's your isenbar? What's the word? No, that's wrong. It's isotherm. We're supposed to go down the isotherm. Well, we can do that. Look at here. Going from 1 to 3. Here's state 3. And you stay on the 800K isotherm, and you get to the same isobar, the 100 kilopascals isobar. So we did a TS diagram, and we did a PV diagram, and we found the work. What about the heat transfer? We got the little W for the, what they call it? The little W for the isentrope. We got. And we got the little W for the isobar. Well, what about the little Q for the isentrope? And what about the little Q for the isobar? Now, one of my excellent students, I can't remember, it might have been Roxana, told us what the heat transfer for the isentrope was. Let me go back to Roxana here. Roxana, was that you that told me what the heat transfer was for the isentrope? Was that you?
No, but I think it was 0, right?
It's 0. Good going. It's 0. She knows it's 0. But now what about the Q for the, wait a minute, we didn't do an isobar. That's wrong. The other process was the isotherm. See here's the isotherm. This is the isentrope. This is the isotherm. Do you notice that, I think I told you guys this, the area underneath your TS diagram is the heat transfer. See, there is no area underneath this isentrope. There's no area underneath it because there's no heat transfer. But there is an area underneath the isotherm. Do you see it? Here it is. It's this tall rectangle. See this rectangle? Here, I'll color it in. You know what that is? That's your little Q. the area under a TS diagram is the heat transfer. And we can get it. Here, let's here we'll make some room here. Now the thing is though, whether it's plus or minus. I got a feeling it's minus. I got a feeling that on the isotherm, he's going to go out. But I'm not sure yet. But here we're going to get the amount. The amount is this area. Now, how do you find the area of a rectangle? Well, you go height times base, right? Well, what's the height? It would be 800 K. That's the height. Now, what's the base? Well, that's the delta S, isn't it? It's not 0 for the isotherm. Let's see if we can do it. I think this would be fun to do. Now, they didn't ask us this. We're going over and above what they wanted. But we could solve for the delta S. See this delta S here for this isotherm? I think we could do it. And here's a lovely equation. It goes like this. Now, instead of me doing it and you guys just being bored watching me doing it, we know all this stuff. We know C sub P. In case you forgot, C sub P is 1004 we know T2 and T1. T2 is 800. T2 is 414.4. T1's 800. We know those. We know R, it's 0.287. Let me write that down. We know R, it's 0.287. We know P2 and P1. P2 is 100. P1's 1,000. We know all of these things, and we could get delta S. And then see if you multiply the height by the width of that rectangle, you can get the heat transfer. Okay, I'm going to shut up now. You know all these numbers. I want you to plug it in, and I want you to get it for me. Now, I'll give you 2 minutes because you're going to have to plug all that stuff in. And we're going to get the delta S, and then we're going to find the heat transfer. Go for it. I'd like everybody to do this. We know all these numbers. We're going to find the change in specific entropy for this process going from 1 to 3. See if you can do it. Well, here's what I got. I wonder if anybody got that. It could be wrong. Anybody getting that? 0.472? Maybe I should do it again. I need somebody out there to say, that's what I got. But I'm not hearing anything. Let me see who's out there. We've got a lot of wonderful students. I never took roll. Here, let me mark down the roll here. Just out of my curiosity, it's nice to know who's here. Today's the 1st of July. Gosh.
This is for us trying to find the isotherm, right?
Yeah, we're doing the isotherm. We're going from 1 to 3. And
Okay. I
I
got
think I did it wrong.
0.661.
I did it wrong. I'm so glad. Who was that just spoke up?
Spencer.
Spencer? You know what I did? This here is 0, isn't it, Spencer?
Yeah, because it's an isotherm natural log of 1 is 0.
Yeah, I bet you did it right and I did it wrong. See, this is minus 0.287 times the natural log. Is it 0.1?
That's what I got.
Yeah. Okay, now let me do that. Yeah, I did it wrong. Spencer, was that your thank you point earlier?
Yes, sir.
Hey, look, you got another one. Keep up the good work. Okay. I'm getting delta S is 0.661. How's that, Spencer?
That's what I got. So I'm hoping that's right.
Yeah, I'm sure it is because I did it wrong the first time. Well, that's kind of fun. We got that. And it came out plus. It came out plus. Now we can get the heat transfer. So you take 800 times delta S. Now, where did that equation come from? I just had a senior moment. And I'm looking at that and I'm thinking, well, where in the heck did that come from? Anybody know? Where did this equation come from? Did it come from the definition of entropy? Basically, it's see, we're just assuming that the atmospheric air is 414. The surrounding air around this cylinder, piston cylinder, is 414.4 K everywhere around it. And so to find the change in specific entropy, there is no, what's the word? There is no generated specific entropy. So it's just that. So the Q is equal to TDS. See, there it is. There's the TDS. Oh, I remember where we got it. This is the area of a rectangle. It's the height times the width. It also comes from the second law, where you have to add the generated entropy, which there is none. And so Q is equal to TdS. Well, there's the T, there's the ds, and now we're going to get our Q. Here goes. It is I don't know if you can see this. It's getting kind of low on the board down there. But I'm getting 528.6. 528.6 kilojoules per kilogram. And it came out to be positive. Well, what does positive heat transfer mean? Does that mean heat transfer in or heat transfer out? And let's go to one of my students here. Aubrey, I think I picked on you already, but let me pick on you again. Aubrey, we think that the heat transfer is a positive 528. Is that going in or going out? You have a 50-50 chance of getting this right, Aubrey. What do you think?
Going in.
Good going, proud of you. So here, let me draw that. There's the heat transfer in. Now let's check this and see if it's right. We'll see if it's right. I need a little room to do that. Here's some room in here. We'll use this. I might have to call on you if I erased something vital there. This is just a check to see if it's right. Now we have a lovely equation that goes like this. We think that heat transfer is 528.6. Now the work now wait a minute. The work we got was 528. But now I'm getting lost now. Was that work for the 1 to 2 or for 1 to 3? What was the work on the isotherm? Oh gee, I hate it, but I think I erased it. Here, let me look. Let me look and see here. The work on the isotherm was 276. I think we had it on the board a little while ago. You guys are taking excellent notes. For the isotherm, is that the isotherm? No. That was the isentrope. The work on the isotherm was 528. Yeah, this makes sense, guys. This is called checking our work. Now, I think we have a round off problem here, but basically, can you see that for the isotherm, the change in specific internal energy is approximately 0. I mean, you got 528 minus 528, that gives you 0. Does it make sense that if you go down an isotherm, that the change in specific internal energy is 0? Does that make sense? Somebody say, uh-huh.
Yes.
Yeah, because see, if the temperature stays the same, the specific internal energy stays the same. Because remember, the change in specific internal energy is equal to C sub V delta T. And if delta T is 0, that's what you got for an isotherm, then delta U is 0. Hey, we checked it. We found the heat transfer. The heat transfer from 1 to 2 is 0, but the heat transfer from 1 to 3 is not 0. It is 528.6. Well, we had a lot of fun with problem 651, didn't we? Wasn't that fun? Okay, now it's 10 o'clock and we're going to take a little 10-minute break now because you're probably tired of this stuff for right now. And we'll come back and we'll have some more fun. We'll start on our second topic for today, which is the second law for control volume. So go stretch for 10 minutes. We'll be back at 10 after 10. Okay? It's break time. Now, if you have any questions, if you're not clear on anything after this break, you can ask me, and I'll try to explain it. Okay, go stretch. It's break time. It's break time. guess the next time I'll be doing this, I'll be in Plainfield. Maybe down there in the playroom office area. Yeah, I need quiet. Yeah. Well, I've got to have a good internet connection. Yeah. Okay, well, let's see. Almost time to end our 10-minute break. But before we before I erase all this wonderful stuff, did anybody want to say anything or have a question? Well, nobody has a question, so I guess I'll say goodbye to all this. I'll leave Spencer's thank you points up there, though. I got a question for you, though. Here, let me ask you a question. We'll see if you guys listen to me or if I just bore you out of your gourds and you don't pay any attention to me. Let me go to my friend. Well, the thing is, I think I've already picked on all of you guys. I think I've lost some people. Did I ever take roll? Let me see here. This is the 1st of July. What about Megan? I don't see Megan on here. Parker, Stewart, yeah. Bear's not on here. Aubrey, Roxana, Cameron, and Spencer. Oh, well. I'm always picking on Stewart. Stewart, the area under a PV graph means something, Stewart. The area under a PV graph means something, and the area under a TS graph means something. Stewart, what do they mean?
Area under a PV is work.
Yes.
And area under a TS, is that heat transfer?
Yes, exactly. That's right. I'm sorry I erased that TS graph because See, we got the area underneath the TS graph. We figured it out. Well, we're moving on now. The next topic for today is the second law of thermodynamics for control volumes. This is really chapter 7. So we are entering into the wonderful world of chapter 7. But let's review the second law for control mass. It goes like this. Should we use big letters or little letters? I like the little letters better personally. That's how the second law for control masses go. And this stands for, but let me just ask you guys. Let's see if you know what it is. Spencer, this delta little s stands for what, Spencer?
That the change in entropy or specific entropy.
That's it. That's it. Good going. It's the change in specific entropy. Good going. Now let's go to my friend Roxana. Roxana, do you see that funny little squiggle? It's a lowercase delta. It's a Greek letter delta. Little delta Q there. And then there's a T there. I want you to comment on what those things mean. Who did I say? Did I say Roxana? Is that what I said? I forget what I said.
I said
Yeah,
heat
Roxana.
transfer rate.
Say that again, Roxana, please.
Is it heat transfer rate?
Yeah, it's not rate though. No, it's not. It's not rate. See, rates have a dot over them. Remember? See, like a Q with a dot over it would be a rate, but this is not a rate. No. It's got heat transfer though. You're right about that. Roxana, that T there, what kind of T is that? Can you tell me what kind of T that is?
Temperature?
Yeah, but would it be, Kelvin or Celsius? What would it be?
Kelvin?
Mm-hmm. It's got to be Kelvin. Or in English, it could be Rankine, but it's not Celsius. And it's not Fahrenheit, is it? Now, that little delta Q thing, you notice it's not written with a, what's the name of that? A definite differential. This is an indefinite differential. Because heat is not a property that exists at an instant in time like properties do. Heat is something that is transferred during a period of time. And this represents a quantity of heat that's being transferred at that temperature in absolute. You can't use the exact differential because see what that represents is a final minus initial. You'll never see me write that. You'll never see me write that because heat doesn't have an instantaneous value. I don't know if you really understand that, but I tried to explain it. And then this here, let's go to my my good friend. I just picked on Roxana. Parker, Parker, tell the gang what this little S with a little gen underneath it stands for, Parker. What does that stand for?
Generated specific entropy.
That's it. It's a generated specific entropy. And it has to do with things like friction, for instance. There's a list. I was reading off a list in your book. You could read that. Talks about irreversibilities. Well, now, we've studied that, but that's for control masses. See, that CM, that stands for control mass. What we're going to study right now is the second law for control volumes. Well, what they did was they took a system that had mass going in and out, and they looked at the rates. They looked at the change in entropy per time. And they came up with this here. Actually, the way the book does it, let me do it the way the book does it. The way the book does it is they use big letters. I like the little letters, but this is what the book does it. This is the way the book does it. And if you divide this through by time, you get this. But see, if you have mass going in and mass going out, you have to include that. Because mass has entropy. Entropy is a quantity just like pressure, a temperature, volume, or whatever. It's a property. And if you have mass, if mass is going into a system, then entropy is going into the system. If mass is going out of a system, see that's the mass flow rate out. It's the exiting, that m dot with a little e there is the exiting mass flow rate. And if mass is going out, say of a turbine maybe, then entropy is going out. And so what we have here is if you divide through by time and you have a control volume, then these terms, you can sort of see where these terms come from. So now we have our second law. Ta-da, and we're done. We got it. There it is. Now we're going to work a problem. Now the one I picked out, let's see if I can find what I picked out here. I picked us out a problem. It's 722. Let's do that one. This is going to be problem 722. Now I don't want to do your homework for you. Let me double check here that I'm not doing your homework. And no, that's not your homework. Great. Okay, let's do that. Let me find it here. And we've got our second law. And we talked about it a little bit. And we're going to do problem 722. That's what we're gonna do. Okay, let me find it here and see what it is, 722. Compressor. Now, I don't know if we've ever done any compressors. I forget whether we've done any compressors or not. But compressors are sort of the opposite of a turbine. They require an energy input. They require a power input. They don't work too good unless you plug them in or provide them with power somehow. So we have a compressor. They're sort of the opposite of a turbine. Now, a turbine, the pressure goes down from beginning to end, inlet to exit in a turbine. But see, in a compressor, it's just the opposite. The pressure goes up. In a turbine, the temperature goes down from inlet to exit. In a compressor, just the opposite. The temperature goes up. You'll see on the PV and TS diagrams for turbines and compressors, they're just backwards. Everything about a compressor is backwards. Now the symbol for a compressor, I'll try to draw the symbol here for you. And let's put in some values here. Now this particular compressor, we're doing 722. It's air. And you have air coming in at 300 K. Let me write that down. And 100 kilopascal coming in. And the pressure goes up to 1,000 kilopascals. See, a turbine is just the opposite. It comes in at high pressure and it goes out at lower pressure. Well, a compressor comes in at lower pressure and goes out at higher pressure in a reversible process. Now, they didn't say adiabatic, but we're going to assume, I'm lying to you a little bit. Compressors can get hot, and they can have a heat transfer with the environment. But we're going to keep this simple, and we're going to assume that this compressor is adiabatic and reversible. And we have learned something about things that are adiabatic and reversible. We have a fancy name for it. I wonder if anybody has listened to me. If you have something that's adiabatic and reversible, they have a fancy name for that. And let's go to my friend Spencer. What do they call it when it's adiabatic and reversible? What's the name of it?
Good question. Is it a Carnot cycle? Or
No. Guess again. It's adiabatic and it's reversible.
I think I have it in my notes here somewhere, but I'm not finding it right now.
That's why I ask you guys this, see? Because I'm going to tell you what it is, but I've told you this before. It's called, I'll give you a hint. It starts off with IS, blah, 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 blah.
Is it the isentropic process?
That's it. That's it. It's an isentropic process. Good going, Spencer. And that's what that means, is that the delta S is 0. But see, we really should use the second law here, let me write that for you. The second law goes like this. Oh, by the way, you're going to have a power input. See, for a turbine, you have a power output. But for a compressor, it requires a power input. Here, let me write the second law. Here it goes. Goes like this. There it is. That's the second law of thermodynamics. For a control volume, and this term here is going to be 0. I'm going to give Spencer another chance here. Spencer, why is that term, the time rate change of entropy, why is that 0, Spencer?
It's 0 because it's a reversible process.
No, that would be this one here.
Or,
What you did was you
oh,
answered.
yeah.
You answered why this is 0, but why is this?
Isentropic means like if the entropy is constant, so the change in entropy is 0.
Yeah, you know what? You're right, Spencer. That's good thinking. That's good thinking. There's nothing wrong with Spencer's answer. The answer I wanted was, though, see what's confusing is these little s's refer to the entropy going in and going out. This big S refers to the total entropy inside your control volume. And it is not changing with time. This morning you had this compressor running and it had so much total entropy in the compressor. An hour, 2 hours, 3 hours later, the total entropy inside the compressor is the same. And so it's not changing with time. You don't want to get confused. This deals with the total entropy inside your control volume. These little s's over here refer to the entropy coming in and entropy going out. Now, the reason why this is 0, the answer I wanted, it's kind of subtle, but the answer I wanted was this is a steady state compressor. None of the properties change with time. The properties change with location. Hey, look at here. You see the temperature going in is 300. The temperature coming out is going to be lower. No, that's wrong. This is a compressor. The temperature coming out of the compressor will be hotter. But that's a change with location, not with time. Whatever this temperature is, we're going to figure it out here in just a minute. Call it T2. See, T1 going in is 300 K. T2 coming out is going to be hotter, but it's not changing with time. An hour later, whatever this exiting temperature is going to be the same. Now here we can get it, because since it's an isentropic ideal gas, we're going to treat air like an ideal gas. We can do this here. We just talked about this. Now you can only use that equation if you have an isentropic ideal gas. Well, we do. It's air. It's an isentrope because it's adiabatic and reversible. That's an isentrope. And air is an ideal gas. And looky here, we know T2. I'm sorry, we don't know T2. We know T1. It's 300. We know P2. We know P1. And we know what they call that, the specific heat ratio for air happens to be 1.4. We talked about that. Now I'm going to shut up for a minute and a half. And I want you to plug this in. I want you to get T2 for me. Every one of you should be working that out for me. Go for it. Well, I think I've got it. How about somebody helping me on this? Anybody out there got it yet?
I got 579.21 Kelvin.
That's what I got. Was that my friend Stuart?
That was Spencer.
Spencer, good going, Spencer. Okay, so we've got the T2 here. Let me write it. It's 579.2 K. Do you notice it got hotter? Look, it came in at 300. It's a compressor. When you compress air, it gets hot. It comes out at 579. Now that's not changing with time. An hour later, it's still 579. An hour later, it's still going in at 300. It's not changing with time. We got the exiting temperature. Now let's get back to our second law. We're going to make this 0 because it's an adiabat. There isn't any heat transfer rate, so it's an adiabat. It's reversible, so that's 0. Now these m dots are the same. So you have m dot Si minus m dot Se. You don't need special subscripts for the m dots. And see if you can get to here with me. Got a bunch of zeros here, and these m dots are the same. Can you see that the little si has to equal to the little se? Can you see that? Because the m dots are the same. And that's what an isentrope is. If the little si is equal to the little se, what that means is the change in specific entropy is 0. Now, what we're talking about here is the change in the entropy entering and exiting, aren't we? See, that's the incoming and exiting entropy. And so we have an isentropic process. We got the exiting temperature. Now let's see what else we're supposed to do with this problem. And let me read this here. It says something about how hot is the exit flow? Oh, we did that. What is the specific work input? Well, to get the power, we would have to know what m dot is, and you'd have to multiply by the specific work. That's a little w. They're asking us for the little w. They don't want the power. They want the little w. Okay, well, let's see if we can do that. I need some room here. Anybody have any questions before we figure the work per mass that has to go into this compressor? Okay, well, here we go. We're gonna need some room to operate here. To get that little w, we're going to have to do the first law of thermodynamics. See, this is how we do our problems. We draw our device sketch. Hey, wait a minute. Oh, I'm forgetting something. What about the PV and the TS diagram? We need to do those. Doesn't that sound like fun? We will in a minute, but here, let me go ahead and write the first law. You guys know and love this first law, but see, this is a control volume. You've got to use this form of the first law. Now there's some other terms here that I'm too lazy to put in, but I don't think we need them. Those terms deal with kinetic and potential energies. And I think it's negligible. I don't think this compressor is moving at all, so it's not changing its kinetic energy or its potential energy. All right, well, this here is 0. Now the answer, if I ask you, how come that's 0? The answer you're supposed to say is because it's steady state. This is a steady state turbine. The properties do not depend on time. This temperature here is 300 going in. Hours later, it's still 300 going in. All the other properties do not change with time. And so the total energy inside your compressor does not change with time. So it's 0. It's a steady state compressor. It's adiabatic, so there's no heat transfer rate with the environment. This is a keeper, though. You've got to have power input. The m dots are the same, so you could just write them like this. Do a little algebra there. Now see if you can follow my algebra here. Why don't we just call it delta H? Well, no, it's negative delta H, isn't it? And you're multiplying, you're not subtracting. See, delta H is final minus initial. Delta H would be HE minus HI, but what we've got is HI minus HE. So that's negative delta H. Okay. Now, if you divide through by m dot, here's what you'll have. And make a little room here someplace. And we'll finish off this problem. They wanted little w. Little w is big W dot over M dot. And that's equal to negative delta H. Did you follow to that okay with everybody? And you know how to do this, don't you? This is C sub P delta T. Well, what's C sub P? For air, it's 1004. And what's delta T? Going from 300 to 579, that looks like 279 to me. 279.2 K. And now wait a minute, there's a minus in front. And so we're going to get our work per mass. Here we go. I'm getting a negative 280.3 kilojoules per kilogram. It's negative. How come it's negative? Do you remember me telling you expansion work is positive, compressive work is negative? Well, this is compressive work. You got a compressor, and that's what I got. Now, I wonder if that's what I got when I did this problem before. Let me look and see here. Which problem are we doing? 722. Yeah, that's what I got before. Good deal. Okay, good. Well, I was real proud of you. Most of you did pretty decent on your exam too. We had a few little snafus, but I think we overcome them. And I put the key on Blackboard. I put it under content. So if you didn't get 100, what that means is your answers are different than my answers. And I have the correct answers under content in Blackboard. Just pull it up, and that way you can look and see, oh, that answer is different than my answer. That's how come I didn't get 100 on that. So go over that. If I cheated you now, you email me and let me know. I don't want to cheat anybody. Okay, well, we did 722, and I think there's some homework, and you guys know how to do that homework. And there's a due date and the homework. It's all on Blackboard. But hey, we got a little bit more time here, and let's do another problem. Those problems were all they were all metric. I think maybe we should do a English problem. Let me see which one I want to do here. Just a minute. We got to know how to work in English, you know. Some of you might get a job in the United States. They still use English there. Okay. Okay, well, I got one here that looks pretty good. Now, before we tackle an English problem, is there any comments or questions? All right. Okay, well, we're going to tackle an English problem. Now this one is, I'm going to erase all this stuff. Now these problems, we only have a half hour left. And the chances are that we won't finish this problem, but oh, doggone it. I was going to do a PV and TS diagram on that last one. Is it too late to do that? It's never too late to do that. Now, which problem was that? That was the compressor, wasn't it? Okay. Let's do that. Because we always do that, don't we? We always do what problem was that? 722? Now, what's the rule? If you have a process, then sketch the process on a PV and sketch the process on a TS diagram. That's the rule. Well, we had a process, all right, but I didn't do it. We might still have time to work on a English problem. Now, unfortunately, I erased all that, but I think I have some of the info here. We know we came in at 1,000. We know the temperatures. The temperatures are 300 and 579, 300. We got all this a little while ago. So this is how you would draw those here. See, that's the 300, 579. Now the pressures. Well, you came in at 100 and you went out at 1,000. So you go like that. Come out here at 1,000. Come in here at 100 kilopascal. There you have it on your PV diagram. Now, what does a TS diagram look like? Well, you've got the 1,000 kilopascals like that, and the 100 kilopascal like that, and there's your. Now they have a name for that process. They have a name for this process. They have a name for that process. And let me pick on one of my wonderful students here. Let's see. There's only 5 of you guys, but my IT person is going to have this on YouTube, and the rest can watch it. Stuart, I'm always picking on you. Stuart, what's the name of this process? It's got a name. It's called a. Go for it, Stuart. It's not an isotherm because I didn't follow the isotherm. It's not an adiabat. Wait a minute. Yeah, it is an adiabat. I think I just gave away the answer. But it's a very special adiabat. What is the name of this particular adiabat, Stuart?
Isentropic?
Yeah, it's an isentrope. It's an isentrope. It's isentropic. Its delta S is 0. Hey, do you see the delta S doesn't change any? The S, the little S just goes straight up. Now, if it was a turbine, everything's opposite. Your 1 would be here, your 2 would be here, and you'd be going down. Your 1 would be here, your 2 would be here, you'd be going down for a turbine. But that was a compressor. It wasn't a turbine. Okay, there I did it. I did my, and you will too. If you have a process, you're going to do a TS and PV, aren't you? To keep me happy. Oh, yes, we will, Mr. Griffin. Okay, well, let's give this a try. Now, this is going back to the control mass problems. But we got to know how to work in English, senor. Okay, now this is 6147E. Okay, now let me read it. Let's go back, find 6147E, and we can at least draw the what do they call it? The sketch. We can draw the device sketch and maybe the PV and TS diagrams. That would be great, wouldn't it? And then we could start on the first and second laws. That's how you do these problems. Let me find it here, 6147. Cylinder piston contains air, it's compressed. Okay, well, let's draw it. We're going to do the device sketch now. The air contains 4 cubic feet of air at 16 psi. Let me write this down. This is state 1. This is state 2. And we have 16 psi, 77 Fahrenheit. At state 2, it's compressed to 120 psi. Wow, pressure went up, didn't it? 400 Fahrenheit. Okay. Assume heat transfer with the ambient at 77. Find the polytropic exponent in. Final volume, work done, heat transfer, total entropy. They want a whole bunch of stuff. But we can get it, we can get a little bit done. I think I made that too narrow. I think it's more like that. There we go. Now we need to decide where to put our piston. And I think I'm going to let you do that. I'm going to shut up for 1 minute. And I want you to put the piston in here. Now it might go up, it might go down. You try it. Put the piston in there, and then I'm going to put it in there, and we'll see if we agree. Okay, you've had a minute. And I'm going to put my piston in there now. Do you notice that pressure went up? My guess is, here's your piston, state 1. And then here's your piston at state 2. Put a heavy weight on there. Look, that pressure went up a lot. See it? That's what happens when you put a heavy weight on a piston, the pressure goes up. And you know what? The volume went down, didn't it? The volume and the temperature went up. Did you know when you compress, it's air, right? Yeah, it's air. When you compress air, the temperature goes up. Now, does yours look like that? Hey, while we're at it, let's go ahead and get the specific volume. Now, the way it works is P1 V1 is equal to RT1. Now, if you know the temperature and you know R and you know P, you can get V1 and P2. V2 is equal to RT2. Well, we know T2, we know R, and we know P2. We can get V2. Now let's give you a minute and a half. This is good practice. We're kind of reviewing stuff here, really. I'm going to shut up for a minute and a half. I want you to find V1 and V2. Go ahead. Well, I got V1, but you might need more time. Let's give you some more time to get it. This is a good review. Roxana, I'm always picking on you. You're such a good sport. Do you have that yet? V1.
One second.
Yeah, take your time.
Is it 9.6 too?
That's not what I got. Now, you might be right and I might be wrong, but that's not what I got. Here, let me write it out for you, Roxana. P1 is 16. Now, R is T is T is But to get the units to work, you have to multiply by 144. Let me do that and see what I get again, see if I get the same answer. Yeah, I'm getting the same answer. Roxana, do you have the answer yet?
Is it 12.4?
That's what I got.
Okay.
Roxana, what are the units of that 12.4? Gotta have units. It's in
Um,
English.
I'm not sure.
That's okay. And that's why I'm asking, because if you're not sure, there'll be others that are not sure. But in English, it's cubic feet per pound mass. Now, I'm going to pick on another student, but I want little v2. I'll shut up again for a minute. See if you can get little v2. Go for it. We'll see if we can pick on Parker. Parker, do you have that little v2 yet?
I got 2.65.
That's what I got. Now, does anybody need me to write that out, or are you okay? If you're not, I could write it out. But here, let's put these. This is 12.43 cubic feet per pound mass, and this one is 2.655 cubic feet per pound mass. Okay, let's draw the TS and the PV and the TS. Here we go. We're going to draw that now. I'm going to erase this if it's okay, unless somebody says, wait, Mr. Griffin, wait, not yet, not yet. You better say it pretty fast, because I'm going to erase it. Nobody said anything. I need this room here for my PV and TS. Okay, well, here goes. This is kind of a little review thing here. All right, now this is going to be the PV. And this can be the TS. Okay, well, let's get some red stuff on here. And why don't we have a 400 Fahrenheit? There it is, a 400 Fahrenheit and a 77 Fahrenheit. And a 400 Fahrenheit and a 77 Fahrenheit. Okay, now we're going from 16 PSI to 120. Yeah, there you go. State 2, state 1, 16 PSI, 120 PSI. Okay. Before I do this one here, I'm going to pause and figure out my delta S. Now we've got a lovely equation for that. I think we know all this stuff. Let's plug in our numbers. We know this here is 1004 or 004. And this has got to be Kelvin, doesn't it? Well, roughly it's 860 over 537. Now this is wrong. This is wrong. That was an SI thing. We're in English, senor. See that E? I think the C to P is 0.24, isn't it? See, that makes it so complicated. I'm sorry, but that's just tough. Okay, now the R, again, they have to make it so complicated. In English, well, it's this here, but see, that's foot-pounds per pound mass Rankine, and we don't want that. We want BTUs. And so you have to do this. To get the BTUs, you have to divide by 778. Foot-pounds. Natural log, now the P2 is what, 120? And you divide by 16. I think that's your delta S. Now, did I ever do that? Let's see. I wonder if I did that right. I don't think I did it. I better stare at that and make sure that's right. Okay. See, that's foot-pounds per pound mass Rankine. And see, that'll get the BTUs per pound mass. The Rankines will cancel, won't they? BTUs. I'm getting confused now, guys. Just a minute. Let me stare at this some more. We want BTUs per pound mass Rankine. That is right, isn't it? Pretty sure. Okay. The pounds. What happened to the Rankines over here? I think it's okay, because I think this is foot-pounds per pound mass Rankine. And so you have Rankines in the denominators on both, and that's good. Okay, well, here we go. We're going to find out what delta S is. Here goes. SI is so much easier, you know that? Well, if I did that right, I'm getting a delta S. It's very small. So what that means is it's going off here to the left a little bit. It's getting hotter. See, this is the 400 Fahrenheit, and this is the 77 Fahrenheit. And here's state one, and it goes off to the left, not much, but it goes off to the left because it's, I forgot my minus sign. I got a negative 0.025. It goes slightly to the left. Now let's look at our pressures. The pressure here is 16. There you go, 16 psi. And the pressure here is, that's the 120 psi. We have just drawn the PV and the TS diagrams. Interesting. And you know what this area is underneath the PV. And you know what this area is here under the TS. Now, let me ask one of my wonderful students if they paid attention earlier. Aubrey, this area represents something under the PV diagram. What is it, Aubrey?
Work per mass.
That is correct. And Aubrey, this area here under the TS diagram represents something. What does it represent?
I don't quite remember.
See, that's good, because now if you don't remember, others don't remember. And this is a little W. I'll give you a hint. It'll be a little something. Aubrey, what do you think?
Heat transfer per mass.
Yeah, it's a little Q. There you go. And in both cases, the answer is going to be negative. This little W is going to be negative because you're compressing. Have I ever told you guys that compressive work is negative and expansion work is positive? I ever mentioned that? What, about 5 times maybe? And so it turns out that the heat transfer is negative also, because you're going here to the left. I think we're going to get a heat transfer that's out, which kind of makes sense. What would really be fun is if we had time to calculate that work per mass and that heat transfer per mass. Now, we don't have time, is the sad thing. But if we did, I wonder how you would go about it. I wonder how you would go about it. Here's how. You would use the first law of thermodynamics, and you would use the second law of thermodynamics. Now, before you could do either one of them, though, we're going to have to find, you're going to have to find the what they call the polytropic constant. They said this was polytropic, didn't they? I lost my place. Yes, they said it's polytropic. So I only have 2 minutes left, but here's, if we had time, here's what we would do. We would go P1 V1 to the n is equal to P2 V2 to the n. Now, don't we know P1? Well, yeah, P1 16. Don't we know P2? Well, yeah, P2 is 120. Don't we know V1? Well, yeah, we figured it out. It's 1243. Don't we know V2? Well, yeah, we figured it out. It's 2.6 blah, blah. Here's an equation with only one unknown. If we had more time, we could do that, couldn't we? Oh, of course we could, Mr. Griffin. We could find the polytropic constant. And once you did, you could find little w because it's equal to P2V2 minus P1V1 all over 1 minus n. And you know all that stuff. We could get little w. Oh, gee. But how would we get little q? Well, in this case here, you would use the first law, but the first law in this case is for control masses. It's q minus w. If you could get little w, delta U is easy. You know how to do that. It's sad though. Our time together is coming to an end. But hey, cheer up. You got homework to do. And read ahead. And we'll have more fun next time. Now, I'm going to go over here where it says, it says goodbye, students. This is your last chance to say something. Go ahead, I'm listening. If you want to say anything, now's the time. 5, 4, 3, 2, 1. Okay, bye-bye, students. Till next time. Adios.